All right. Hello, everyone. Welcome back. And then, we are going to start the afternoon session. And then my name is Takahiro Harada from AMD. And then first paper is online. And then authors couldn't make it. And it's this one, non-uniform point cloud upsampling via local manifold distribution. And then I guess they recorded. Okay, let's listen.
Good afternoon, distinguished attendees. My name is Fang Yahui in EAF from Beijing Normal University. It is a great honor to have the opportunity to present our recent work entitled Non-Uniform Point Cloud Upsampling via Local Manifold Distribution. The first part is the introduction. Point clouds are an effective data structure for representing 3D objects and have been widely adopted across various fields. However, due to practical limitations during the scanning process, such as object field occlusion and environmental constraints related to position to a world, point cloud data inevitably suffer from issues such as pulse, sparsity, and noise. These imperfections compromise both the completeness and clarity of the point cloud, which in turn adversely affect the performance of downstream processing tasks. Point cloud upsampling serves as a fundamental processing step to enhance the density, uniformity, and structural regularity of point cloud data, thereby providing a solid foundation for subsequent applications. For point cloud upsampling tasks, the objective goes beyond simply generating dense and uniform point sets from sparse inputs. More importantly, upsampled points should closely adhere to the underlying surface geometry. However, when the input point cloud is highly sparse, the gaps between neighboring points become increasingly pronounced. Traditional upsampling methods that rely primarily on spatial coordinates often overlook the intrinsic distribution characteristics of the point cloud, leading to uneven or clustered results when processing sparse and non-uniform point clouds, as illustrated in the figure. Several existing methods produce visible point clustering in such scenarios due to the non-uniform nature of the input data. To address this issue, we leverage the probabilistic nature of point clouds and adopt the concept of statistical manifolds. Specifically, we construct a unified statistical manifold by fitting a Gaussian representation within each local neighborhood and impose distributional constraints on the manifold to guide uniform upsampling. The definitions related to statistical manifolds are presented above. A statistical manifold is a manifold space composed of a family of point cloud probability distribution functions. Next, we present the main components of our proposed method. The overall framework is illustrated in the following flowchart. We introduce a novel representation of point clouds by interpreting them as samples drawn from underlying probability distribution functions and construct a statistical manifold framework to model the geometric structure by building local manifold representations and enforcing distributional constraints via geodesic distance. Minimization. Our method generates more uniformly distributed points. We begin by treating the local neighborhood around each projected point as a two-dimensional manifold, embedded in three-dimensional space. Since the manifold surface in 3D space is homomorphic to a 2D region, this local coordinate system for each point and its neighborhood such that the neighborhood can be mapped to a two-dimensional Euclidean space via homeomorphism. Within this local coordinate region, we define a set of truth chip parameters centered at this point and use Gaussian functions to fit the local neighborhood of the point cloud by performing Gaussian fitting for the neighborhoods of various query points and mapping them onto a two-parameter manifold. We are able to construct a unified statistical manifold for the point cloud in formulation. Each point corresponds to a probability distribution of the manifold, and the overall structure and geometries of the point cloud can be modeled through statistical representation. The geometric structure of the point cloud is thus included within the Gaussian functions, providing accurate local geometric guidance for the subsequent Euclidean point tree Symposium. Furthermore, we incorporate point distribution information to guide the generation of upsampled points. Based on the statistical manifold constructed from Gaussian representations, we propose a novel correction mechanism for point cloud distribution. By minimizing the geodesic distances between corresponding points on the manifold, we impose constraints that guide the upsampling process. This ensures that the generated point cloud more accurately recovers and preserves the details and shapes of the original data in order to make the upsampled point cloud closer to the distribution of the true value. It can be translated into the closer the distance between the two corresponding points, the statistical manifold. Here we pick the geodesic distance between the two distributions. This geodesic line is defined under the Fisher information matrix between the distributions. The equations shown in the figure represent the Fisher information matrix and the Fisher raw distance between two multivariate molar distributions, respectively, to constrain the distribution of the point cloud. Our objective is to minimize this distance. In the section, we present several visualization results and quantitative metrics to demonstrate the effectiveness of our method. We showcase upsampling and surface reconstruction. Results on several models where the original point clouds contain 124 points and are upsampled by a factor of 4 surface reconstruction. We adopt the Poisson reconstruction method, as shown in the visualizations. Our method produces smoother and more uniformly distributed points compared to other methods, particularly on geometrically complex models such as the alpha. The improvements in upsampling significantly benefit the subsequent surface reconstruction, effectively filling in gaps that remain problematic for other methods, which often results in noisier and more irregular point distributions. Quantitative comparisons are provided in a complementable method consistently achieves superior performance on disperse and non-uniform point clouds. Across most evaluation metrics we compared with existing methods, we further evaluate the performance on sparse and non-uniform point clouds with different input sizes, specifically 256 and 496 points. As shown in the table below, our method slightly underperforms React KPU in certain metrics, such as HD and P2N. At the 256 point level, the visualization results clearly indicate that React KPU yields highly uneven distribution under extreme sparsity, whereas our method maintains better uniformity and surface covering. To assess the robustness of our method to noise, we conduct experiments under 3 noise levels 0, 5, 1, and 2. The visual results demonstrate that our approach effectively constrains noisy outliers to remain close to the underlying surface. Moreover, our method consistently achieves the best uniformity under varying noise conditions. Finally, to validate the real-world applicability of our method, We conduct experiments on a KT dataset. Due to the absence of ground truth point clouds, we provide visual comparisons. Even when applied to real-world current data, our method successfully fills in missing regions and outputs more uniformly distributed points, demonstrating strong generalization capability. Finally, our conclusions are summarized as follows from the perspective of statistical manifolds. We have pioneered the construction with an upsampling model of point cloud spatial structure and probability information based on the probability distribution characteristics of spatial point cloud data. By constructing statistical manifolds, we can better simulate and understand this generation process and model the distribution characteristics of the point cloud through the local manifold representation of the point cloud and the geodetic distance constraint. The upsampled point cloud can better camera and maintain the details and shape of the original data, maintain the consistency of its shape and detail, and generate more uniform points. That's all for my report. Thanks for listening. I sincerely hope for your valuable suggestions and comments.
All right, then. Is there any question from the audience? Oh, there you go. Oh, cool.
Hi, Yohui, can you hear me? Hi, Yohui, can you hear me?
Yes, I can.
I wonder, how do you balance your uniformity constraints with preserving fine detail like sharp edge or the complex textures during the point cloud upsampling?
Yeah.
Can you hear me?
Say again?
Okay. Hi. Can you hear me? Okay, I will start my question. Can I start asking my question?
Okay.
I'm wondering how do you balance your uniformity constraints with preserving fine details like sharp edge or complex texture during your point cloud upsampling?
Okay, thank you for the question. We have thoroughly considered this issue in the design of our method. Although the primary purpose of the distributional constraints is to ensure point cloud uniformity, we have employed several mechanisms to preserve the geometric details. First, during the local Gaussian filtering stage, we allow each local neighborhood to optimize the parameters of the Gaussian functions based on its own point cloud distribution, meaning that each local region can return its unique geometric characteristics. And second, we introduce a first-order derivative constraint in the optimization process, which helps to smooth surface transitions while avoiding interference from outliers. And our method integrates both global and local distribution information, guiding the point cloud distribution through statistical manifold constraints rather than simply enforcing uniformity.
Okay, thank you. Okay.
Okay.
Anybody else? If no, maybe I can ask one question. So you showed like a bunch of like good results, right? The results you showed are very high quality. Do you have any corner cases you are aware of for your method?
Okay, thank you for your question. And I say, in fact, our method employs a local Gaussian fitting strategy when constructing the statistical manifold. We introduce distributional constraints by minimization the Fisher-Rao distance between corresponding points on the statistical manifold, which further optimizes the point cloud distribution to better approximate the true situation. By fitting the local neighborhood with Gaussian functions, the mean and the matrix of these functions can effectively capture the central tendency and the direction of spread of the point cloud. Okay.
All right. Yeah, thank you. Any other question from the audience? Yes, please go. Please come.
Can you hear me?
Yes.
Okay. You mentioned that the construction of the statistical manifold is used to guide the uniform upsampling of point clouds. However, in practical applications, the distribution of point clouds can be influenced by various factors, such as the precision of scanning devices and the complexity of the scanning environment. How can you method ensure that the statistical manifold accurately reflects the true distribution of point clouds in these complex and variable real-world scenarios?
Okay, thank you for your question. That is an excellent question. In fact, our method employs a local Gaussian filtering, and we have thoroughly considered this issue in the design of our method. First, by selecting appropriate query points and constructing local coordinate systems, we issue each local neighborhood can be effectively mapped to a two-dimensional parameter domain, and then by fitting the local neighborhood with Gaussian functions, we allow each local neighborhood to optimize the parameters of the Gaussian functions based on its own point cloud distribution, and we introduce distributional constraint by minimization the Fisher-Rao distance, and introduce first order derivative constraint in the optimization process. Therefore, when dealing with models that have sharp edges or complex textures, our method can effectively balance uniform distribution and geometric detail retention, as demonstrated by our experimental results. Thank you.
Okay, thank you. Good answer.
All right, then thank you very much. And then let's thank the speaker, Yao Fui. I guess it's very late for you to stay up till this time. All right, so the next presentation is Arya Patel. Okay, your paper. The paper is Normal Guided Detail Preserving Neural Implicit Function for High Fidelity 3D Surface Reconstruction.
Hello everyone. My name is Arya Patel and I will be presenting our work titled Normal Guided Detail Preserving Neural Implicit Function for High Fidelity 3D Surface Reconstruction. I'm a PhD student at IIIT Delhi, India, and this work has been done in collaboration with Dr. Hamid Laga, who is from Murdoch University, Australia, and my advisor, Dr. Ojaswa Sharma. So yeah, let's begin. We address the problem of 3D surface reconstruction from multi-view RGB images. The inputs of our method are multi-view RGB images of a particular scene, and our method outputs the surface reconstruction of the scene. In the following image, we can see images of different objects followed by their reconstruction obtained by our method and the previous methods. So we basically handle both kind of input multi-view images in sparse setting as well as the dense input RGB images setting. So neural implicit representation have emerged as a powerful paradigm for 3D reconstruction. However, despite their success, existing methods fail to capture fine geometric details and thin structures, especially in scenario when we have sparse multi-view RGB images of the objects. And moreover, previous method often required training on a large number of input views. As can be observed from the image, the newest method fails in sparse view scenario, and the RNB newest method is unable to reconstruct complex geometry. So our contribution are the following. We show that training neural implicit representations with surface normal lead to highly accurate surface reconstruction, even when we have as few as 2 RGB input images. Using input multi-view RGB images, we compute the approximate ground truth surface normal from depth maps, which are produced using an off-the-shelf monocular depth estimator, which is depth anything. During training, we directly locate the zero-level set of the SDF network and supervise its normal with the one estimated from the depth map. And extensive experiments demonstrate that our method achieves state-of-the-art reconstruction even when we have a minimal number of input views on various multi-view datasets. So here is an overview of our method. Our method involves the following steps. We cast camera rays from each pixel into the scene while sampling n points along the ray. And for each and every point sampled on the ray, we basically find the corresponding SDF value and the rendered RGB color value using our SDF network and the neural renderer network. So here, both the SDF and the neural renderer network are basically MLPs, and they have around 4 layers. Then once we have the color value for each and every sampled point along the ray, we use volume rendering in a differentiable manner to find the rendered color of each pixel. Finally, we additionally supervise our method with the depth normal consistency laws, which enables 3D reconstruction of intricate geometric details and thin structures. In order to compute our depth normal consistency laws, we first obtain the approximate ground truth normal image by using a monocular depth estimator, which is depth anything, to get the monocular depth for each input image. Then we take the derivative of the depth map to get the normal image. We treat this normal image as the approximate ground truth. Then finally, we estimate the normal map by taking the gradient of the sign distance function at the particular surface point, which acts as our estimated normal image, and we compute the loss between the pseudo ground truth normal image and the estimated normal map. So here we have a more detail on our depth normal consistency loss. We measure the depth normal consistency loss between the ground truth normal and the rendered normal as shown in this particular image. So we take an average over m pixels which are sampled from that particular image, and we take the L2 loss between the normals which are estimated by depth anything method and the one estimated using our method. And we also make sure that both the normals are in world's coordinate space. So we basically use a transformation matrix to transform the approximate ground truth normals from camera coordinates to world coordinates using this transformation matrix T. The total training loss is the weighted sum of color, iconal, and depth normal consistency loss. So the photometric loss measures the L1 loss between the ground truth pixel and the rendered color, and it is computed using the given formula. So here M is the number of pixels which are sampled from the image, and here we take the L1 loss between the ground truth color value and the predicted rendered color value. Then we also have our iconal loss, which makes sure that the learned SDF is a valid distance field. So this is computed by ensuring that the gradient of the signed distance field, which is a normal vector, so the norm of the normal vector should be 1. So here we have the iconal loss, which makes sure that the SDF is a valid distance field. Finally, our total loss is the weighted sum of all three losses. Now we see the qualitative results on one of the data sets, which is the Diligent MV dataset. So this figure shows the reconstructed 3D meshes and the corresponding angular error for two objects from the Diligent MV dataset, and we compare our method with the previous methods. Here the normal mean angular error, which is shown in the second row of both the images. So it is we compute this error by taking the per vertex angular error between the ground truth and the reconstructed mesh. And the more blue the color is, the lower is the angular error between the normal vectors, and better the normals align with each other. And the normal mean angular error is also clipped at 45 degrees for visualization purposes. We can see that our method produces the most accurate geometry and the lowest mean angular error across both the objects of the dataset. Here are some additional results. So here we can see some zoomed in reconstructed mesh patches for our method and the previous method for the given input image that we have of that particular object into consideration. And the methods which are highlighted in green in the top row, those methods are the MVS method, multi-view stereo methods, while the methods which are highlighted as black, they are multi-view photometric stereo methods. So across all the methods, our method gets us the best reconstructions, which is closer to the ground truth. Here we show, in this particular image, we show the performance of different methods when we vary the number of input views from 2 input views to a total of 20 input views. So it can be observed that the performance of the previous methods degrades as the input views become sparser. So for example, for 2 input views, you can see that the chamfer distance, which is a metric for computing the reconstruction quality, it is very high for other methods. This metric should be as low as possible. So other methods have a very high chamfer distance, meaning that they don't get a good reconstruction quality, while we can see from the graphs that our method, even when we have as few as 2 input views, our method gives us very stable results, and this trend continues as we make the number of input views more denser. Now we see some quantitative results on the Diligent MV dataset. So in this table, we have two metrics. One is the chamfer distance metric and another is the normal mean angular error metric. So both the metrics for better reconstruction quality, both the metrics should be as low as possible. And we have compared our method with the previous methods, and across all the objects that we have in this particular data set, we can see that our methods gives us the best chamfer distance and the normal mean angular error value. So now moving on a different data set, which is the sparse DTU data set. So in this particular data set, we have two different settings, and in both settings, we only have 3 input images. So one of the settings is the little overlap setting, where we have very little overlap between the input views that we had. And another setting is the large overlap setting, where we had a large overlap between input images. So here as well, we can see that in most of the scenes that we have in this particular data set, our methods gives us the lowest chamfer distance value for each and every method. And also we get the smallest mean chamfer distance value across the data set. Here we look at qualitative results on the sparse DTU dataset. So we were interested in comparing our method with a state-of-the-art surface reconstruction method, which uses 3D Gaussians for performing surface reconstruction. So its name is Gaussian Surface. So Gaussian Surface is a SIGGRAPH 2024 paper, and they have trained their method for surface reconstruction on dense views. So we were interested in looking at how their method performs when we only have sparse views. So here we only have 3 input views of the given scenes. And we can see that Gaussian Surface produces very noisier results on a sparse view setting, while our method achieves decent and stable reconstruction quality results here. Moving on to the ablation study that we had performed. So we were interested in looking at the effect of our normal supervision in our whole pipeline. So in the following image, you can see in the first column, we have the number of, we have the different data sets that we have, and we have shown a single representative image for them. While in the subsequent columns, in the first column, we first see the surface normals when we don't use the normal supervision. So here we can see that the surface normals are have some artifacts and they are a bit noisier. While if we incorporate our normal supervision, we can see that we get the surface normals, which are very accurate, and they basically are able to reconstruct the whole geometry of the input scene. Secondly, we were interested in performing an ablation study to see whether if we only use a single MLP for outputting the SDF value and the color value versus the full setup that we have, which is composed of 2 different networks. One is the SDF network and second is the neural renderer network. So in the first column, you can see the corresponding input that we have. And in the second column, we show the reconstruction quality results when we are only using a single MLP to output both the SDF value and the color value. So here we can see that the reconstruction has some artifacts, and the results are noisier. They aren't able to basically show the geometry of the input scene. While we see that when we use the full 2 MLP network, we get better reconstruction quality. The third ablation study that we perform is to check the effect when we have different number of input views. So here we vary the input views from 2 views till 20 views, and compare our method with the previous methods, which are surface reconstruction methods. So here we see that even when we have as few as 2 input views, which are the front view and the back view of that given input scene, our method has very good reconstruction quality, while other methods like NEOS, PSNerf, RNB NEOS, their reconstruction quality degrades when we have as few as 2 views. And this particular trend continues as we make the number of input views more denser. Talking about the limitations and the future works of our method. So one of the limitation of our method is the computation time. So like most neural implicit surface reconstruction based methods, our method takes around 8 hours on to train on basically a given input scene. So we would be interested in exploring CUDA based optimization to basically reduce the computation time for our method. Yeah, here are some of the references of our method. Yeah, and thank you for your time. Thank you so much.
Thank you, Arya. All right, then is there any question from the audience? Yes.
Hi, great talk. My question is about the component when you use estimated normals from depth anything. What happens when depth anything fails? Because this is a learned method which is not 100% robust. So when it fails, does this additional depth normal supervision actually hurt your results as compared to if you didn't have this component?
Right, that's a good question. So basically, we whatever data sets that we used, on some of the examples, we saw that when we didn't get good normals as it should be expected, the overall reconstruction hampers because of that. So like our methods doesn't perform well in those particular cases. So yeah, this was observed in very few cases, while our like normal extracting of our surface normal method from depth map is very robust, but for few cases it did fail. Yeah.
Can you also go back to the slide where you're just showing like normal supervision like effect? You show like 4 columns, right? Can you go back? There. So the second column is, can you go to the next one, I think? Second one is like without normal, and then, okay, what are these like 2 columns?
Okay. So here the, I mean the third column here is the one where we estimate the normal maps by using like alpha compositing. So like if the people who are familiar with NERF, so NERF uses alpha compositing to compute the pixel color for each and every sampled point. So in the same way, here we basically use alpha compositing to basically estimate the normal for that particular pixel. So that is the third column. And the fourth column is our method to estimate the normal map. So since we have SDF values for each and every sample point, so let me show this figure. Right, so here for a particular pixel, we have sampled n points along that particular ray. So we have SDF value for each and every 3D point using our SDF network, right? So we compute the normal of that particular corresponding pixel by finding 2 points such that the SDF value of the first point is greater than 0 and the SDF value of that subsequent point should be less than 0, because then we would be knowing that the 0 level set is between those 2 points, right? Then we use the linear interpolation to find the corresponding surface point, And once we have the surface point, we take the normal by taking the gradient of the sign distance field on that point to get the normal. So that is the fourth column that we had.
All right, thank you. Thank you for
Yeah.
clarification.
Thank you.
Can I just ask a small question about experiment? So can I go to the table? Like, did you only experiment on the object is shown here, or you just have experiment based on the whole data set?
Experiments have been performed on the whole datasets, not specific to any objects. So we have performed our experiment on diligent MV dataset, sparse D2 dataset, and blended MVS datasets.
Okay, so the main is for the whole data set, not only for the array.
This particular table, right?
Yes?
Yeah, this is in the first row where the scan IDs are written from 24 till 122. So those are the different objects that are present in the data set, and D2 data set has these 15 objects. So we have performed our reconstructions on all the data, on all the objects within the data set.
For only the objects here. But
Sorry?
you said for only the objects here, or like?
Yeah, so as many as objects are present in the data set, we have performed our reconstructions on all the data, on all the objects.
Okay, thank you.
Yeah.
Any other question from the audience? Maybe another question related to the previous question, but like how reliable is like this depth anywhere module?
Sorry.
What was the module you used to estimate the depth?
Okay,
everything.
It's depth anything.
Okay. How is the quality so far from your experience? It's
Right.
mostly reliable, or that's kind of like okay-ish? Or?
As far as we used for these three datasets, it was very much reliable. So depth anything was a very recent method. It was accepted at CVPR 2024, and we tested a bunch of different monocular depth estimation methods, and found out that depth anything was the best to get the depth map and subsequently the normal map.
Thank you. Maybe we have a bit of time for last question, if there's anybody. Or maybe I'm going to ask another question. So you mentioned that the training time is so long. And where is the bottleneck for your training?
Okay, so actually, if you look at, so this is an optimization based technique. So this particular R method and the other surface reconstruction based methods, they what they do is that they optimize per image. So they take the whole input image and then they sample rays from each and every pixels, and then sample points. So I mean, this particular step of taking the inputs and then sampling the rays and the points, this is this is time consuming, and this happens for over 300k iterations. So I mean, each iteration takes about, I would say, 15-20 seconds. So I mean, that is why we have so much time.
All right. Thank you.
Thank you.
All right, then, if there is no more questions, let's thank Ari again.
Thank you.
All right, cool. Let's see. So the next paper is improved stochastic texture filtering through sample reuse, and then how do I pronounce your name? Bart? Okay. Bart from NVIDIA is going to give a talk about his paper.
Hello, everyone. Welcome to our talk, Improved Stochastic Texture Filtering Through Sample Reuse. I'm Bart. I'm research scientist at NVIDIA, and this work was joint work with Matt Farr and Thomas Akeninen-Müller. In this work, we aimed to address one of the key limitations of our last year's I3D paper, filtering after shading with stochastic texture filtering. This paper was worked together with Matt Farr, Marco Salvi, and Marcus Fajardo. This paper started with a simple goal where we were working before on neural texture compression, and we couldn't afford to fetch multiple samples from this representation. For example, for trilinear filtering, running neural network 8 times would be prohibitively costly. And at the same time, obviously, hardware doesn't support those experimental research novel representations. So we ended up instead approximating texture filter integral by taking literally just a single sample and relying on spatiotemporal filtering to smoothen it out. And this project started as looking at those properties of this estimator and how it changes the appearance. And we realized that the rabbit hole is very deep. We found evidence of similar practices going for decades back in computer graphics, and we ended up formalizing them. And collaboration with Matt Farr and Marcos Fajardo was that it's actually also useful for offline rendering. And here is an example. We're using a stochastic tricubic filtering, so approximating tricubic filter that would otherwise require 64 texture samples. We approximated it with 1 texture sample, and we got both better performance and much better quality than trilinear filtering on volumes. So yes, the idea of the technique was that we approximate texture filters with single texture sample. However, because we are now filtering after shading has happened, we call this filtering after shading, where the order of shading or rendering functions such as BRDF or light interactions is swapped with the order of averaging texture samples. And in our paper and in our talk, we argue that this is always desirable for the task of minification because it approximates supersampling, and it's always desirable. It provides better appearance preservation as well as anti-aliasing. However, the key problem was that while it's great for minification, the results for magnification are mixed at best. There is still some leftover noise, even after applying TAA, or sometimes even DLSS. But most importantly, the appearance changes. Appearance changes as compared to traditional texture filtering. And also, because now we are performing filtering in a different resolution, there is effect of aliasing, which is visible in the screenshot by this kind of ugly, bilinear, kind of diamond-like artifacts, which don't look anything like the ground truth. And this was a problem in practice, meaning that now neural texture compression and stochastic texture filtering is not an easy drop-in replacement for existing texture compression methods. It changes the appearance and it changes the art intent. So we pose a goal for ourselves, or rather 2 goals. First, smaller goal was that, okay, maybe we can still minimize the amount of leftover noise. But the more important goal was that we actually want to make this method more practical with, let's call it, legacy assets or existing assets. And we want to get closer to filtering before shading, traditional texture filtering. And the question is, can we achieve both goals without taking multiple texture samples per pixel? And since I'm giving this talk, you can imagine that the answer is yes. And here is a teaser. At the top row, we can see the bilinear filter. I showed you part of this in sets earlier, where stochastic texture filtering, even after denoising, is still a bit noisy and it changes the appearance. And our new improved method, even without denoising, has significantly less noise, and after denoising preserves appearance very well and has PSNR score of approximately 48, which is perceptually indistinguishable from ground truth. It works not only for bilinear filters, but also for other positive discrete filters, such as bicubic B-spline filter at exactly same cost single sample. And here the bottom row shows how it looks with the B-spline bicubic filter. And to explain our method, let's go back to the key insight that allowed us to develop it. The key insight is that neighboring pixels filter and use almost identical sets of pixels, especially after high enough magnification. The more you magnify, the more shared or similar sets of text cells will be shared by nearby pixels. In the extreme, if you go to infinite magnification, every pixel will filter exactly same sets of text cells. So we would like to do spatial sample filtering, not color or radiance filtering. And we know now that, or the intuition is that neighboring pixels are likely to have the right text cell samples that we need for correct filtering. And how do we do this efficiently? We would not want to split the material pass. We would not want to store all the input text cells in some buffers. This would be prohibitively costly. We considered using group shared memory, but if you ever program compute shaders, you know it's tricky, you need to synchronize, there are bank conflicts, it's complicated code, it's often architecture dependent, and it still costs something. Luckily for us, there is a relatively new, whereby new we mean from 2021, cheaper alternative. It came in the form of HLSL Shader Model 6.0, and Vulkan has similar extensions, namely wave intrinsics. And as a very quick recap of wave intrinsics is that they are breaking with the existing SIM-T model of shader programming, where you program just one pixel or one vertex or one thread in a compute shader. Instead of it, you get exposed to the real nature of GPUs, which is more like SIMD on CPU. You can access whole vector of different threads. And a single thread is called lane in this terminology, while vector of threads is called wave, or NVIDIA's terminology is warp. And the size of wave or this vector is hardware dependent. The most common is 32. And this is what we used in our work as reference, but our work generalizes to any sizes. And the most interesting to us and applicable here intrinsic is wave read lane add, which is very similar to SIMD shuffling or swizzling. And you can access register or variable from any other thread or lane in another thread. But it's much more easier to program and elegant than SIMD shuffling. If you ever program those are not very nice. And I will skip all the details, but some special care is needed for inactive lanes. And it works in all shader stages, what surprised us even in ray tracing shaders. However, for those, the layout is kind of undefined. And in pixel shaders, you can always rely on the quads and helper lanes, and there are even special intrinsics for pixel shaders. And with wave intrinsics, we can obtain texture samples from other lanes without any off-chip memory traffic or synchronization. And this gives us first takeaway. I will scatter throughout my talk some takeaways that I hope are applicable even if you don't care about texture filtering. First, the first takeaway is that you don't have to rely on post-process image filtering. With techniques like wave communication or even splitting passes, you can efficiently use or reuse arbitrary data. And specifically with wave communication, you can do this even in the middle of a complicated material shader. And domain-specific filtering, such as filtering of samples, can be not just cheaper, like in this case, but also yield much better quality. And tomorrow at the keynote, Chris Wyman will talk a bit about how filtering Monte Carlo samples allowed for real-time ray tracing revolution. So here is a very high-level overview of the algorithm. The pseudocode on the right is actual code, but let's not focus on this specifically on code. It's rather to show you how simple the technique is. The technique consists of four kind of main steps or main stages. We're assuming that we're inside of a material shader, and we begin with taking a single texture sample using vanilla stochastic texture filtering. Then we are iterating over some other lanes in the wave and collecting texture samples, PDFs used to take those samples, as well as neighboring UVs. Then we combine those samples together using this collected information, using a Monte Carlo estimator of the filtered value, and we continue with the rest of the material shader. And I will talk about steps 2 and 3 in detail, but let's start actually with the step 3, because it's more difficult and kind of non-obvious. How do we combine those different texture samples? because they are taken from different distributions. Different pixels have slightly different UVs on screen, so the probabilities of taking those text cells will not be identical at the target lane. So the first idea for combining samples taken with mismatch of probabilities is kind of obvious, right? Just use vanilla importance sampling. So we take the text cell value times the filter function divided by the probability of taking the sample, and we do a sum over all the incoming lanes. And this importance sampling estimator, if we have only one lane, the target lane and the source lane, the filter function is the same as probability, they cancel each other out, and we end up with vanilla STF. However, when we try to apply this for collecting multiple samples from neighboring lanes, the results don't look great. Maybe the specular highlight is actually nice in the middle, it's better preserving the shape, but there is a lot of noise. And there is a lot of noise where there was zero noise before. So what's going on? So we begin by analyzing the original STF estimator and STF's error, because it's not like other Monte Carlo integration errors and problems. First of all, STF estimator often has exactly zero error, zero bias, zero variance, and this happens, for example, on constant texture regions. And this is because texture filter weights sum to 1, and STF selects one of the text cells. And maximum error is going to be bounded by the local minimum and maximum values. And we are selecting one of those, and the true filtered value is in between. So if the maximum and minimum value of text cells is the same, which happens in the constant region, then the STF error is exactly zero. STF's error is isolated to edges and high-frequency regions. By contrast, importance sampling error is unbounded. Here we have this division of the filter function over the probability function, and because of the possible probability mismatch, or rather, we know that neighboring pixels have different probabilities, this value is unbounded. It can be arbitrarily small or arbitrarily large, meaning that now those weights will not sum to 1, even in constant regions, and this causes noise. So how do we fix this? So one can first try to hack it. Oh, okay, so first, before fixing it, so what are the estimator goals? Goals are following. We want to never introduce error when there was zero error. We want to never increase the STF error, always improve upon it, and reduce it when it was visible. For example, filtering after shading and before shading difference, we want to reduce it. So the first idea was like, okay, we can hack around the importance sampling. We can clamp the results to the local texture values bounding box. And this is a biased technique similar to Firefly reduction or temporal anti-aliasing clamping. It actually fixes a lot of issues. But we didn't stop here. We were not satisfied with this. We also evaluated other state-of-the-art Monte Carlo estimators. I will refer you here to the paper for details. I'll just mention that we evaluated multiple importance sampling, a cheaper alternative of pairwise multiple importance sampling, as well as Owen's regression estimator that's based on control variates fit to the linear regression. But before we compare all those techniques, we actually have a much simpler and much better alternative than all of those, without hacks. So to introduce our estimator, let's very briefly rewrite the importance sampling estimator just as weight times text cell value, combining those remaining terms together. And the idea was actually the first thing we tried before anything else, just after we saw the problem with the importance sampling. Just normalize the weights. Just make them sum to 1, right? And this means that weights are always bounded. They always sum to 1. On constant regions, there is zero error. And this is not a new idea. This is called weighted importance sampling. And this estimator has been used in history of computer graphics in many applications. It's a biased estimator, but it's consistent and it converges. And what we did, and we believe this is novel, we generalize weighted importance sampling to multiple different sources of samples. And this modification, unfortunately, is not just biased, but it's also not consistent. It does not converge because some of the weights can be zero. However, in practice, the error and bias are very small. It's zero error on constant regions, and it fulfills all of our goals. The worst kind of error of this estimator are those like single, sometimes pixels, especially with large filters like bicubic filter, coming from, they look like fireflies, but they come from the fact that if the original weight of one sample was very, very high, after normalization, it will completely dominate other samples and we will not get any sample filtering. And please see the paper for detailed convergence analysis and other estimator improvements, for example, one that we called exact filtering. So let's have a look how they perform and compare. On the left is a plot of convergence of different estimators with PSNR as a function of samples per pixel. Our estimator performs the best. Similarly, on the right, on the plot with the increasing zoom factor and just single sample per pixel, our estimator performs the best, with the Owens regression estimator being very second closest. There are two interesting things in this plot. So first of all, we validate our initial intuition that the higher the zoom factor, the more opportunities for sharing and the quality increases. And the second observation is that if we look now in this plot at the STF estimator marked with the red dashed line, we see that all of the estimators except for ours and the regression estimator under some zoom factors are actually worse than STF. So they are useless for our application. And we also compared them qualitatively and visually. Again, please check paper if you want to see this figure in detail. What's worth mentioning here that our estimator looks very visually similar to the regression estimator. It has slightly higher quality, but I wouldn't obsess over like, half a dB of PSNR, whatever. But it's much simpler and much cheaper. The second takeaway from this talk that goes beyond texture filtering is that different Monte Carlo integration problems have different error characteristics. They might benefit from different estimators. Make sure that you understand your problem and not just blindly apply state-of-the-art estimators. They might not be state-of-the-art for your problem. A biased or even inconsistent estimator can perform much better than unbiased ones. And the reason for this is that you need to consider other sources of bias, such as denoising, nonlinearities applied, downstream use. Combined bias might be smaller. For example, see the paper supplement for explanation how nonlinearities turn variance into bias. Okay, so now we know how to combine samples from different lanes. How do we choose those lanes? So what are desirable properties of a source set? So let's start with some intuitive ideas. So we have one constraint, that the grid of possible lanes that we can select from is fixed on screen. We cannot read outside of it. It's, for example, here we have 32 lanes configured by 8x4, and we cannot read outside of it. We have to read from within it. But some intuitive properties. First of all, we would like this set to be local, right? The closer pixels are on screen, the closer the UVs, more opportunities for sharing. And second intuitive idea is, okay, we want them to be large. More sharing means more samples, means higher quality, and PSNR seems to confirm it. The higher we go, the higher the PSNR. However, what's worth noting is that because we have this fixed screen grid, it means that now some of the lanes will have exactly same source input of other lanes. They will be filtering exactly same sets of texels. And this introduces correlation. This means that the higher we go with the pattern size, the more we observe those square-like or streaky patterns, despite increasing PSNR. And it's not just perceptual problem. It's also very challenging for denoising. For example, TAA always struggles with denoising 3x3 and 4x4 patterns. While DLSS, DLAA always denoises them perfectly, DLSS balanced, which does also super resolution, not just anti-aliasing, has a camera angle dependent behavior, which is quite annoying to debug. It's a learning-based method, so it sometimes recognizes those patterns as features and sometimes denoises them. But now we understand that we cannot just blindly increase the pattern size. We have a new third property that we want to preserve. We want low correlation. We want low spatial correlation between neighbors to avoid them sharing same sets and producing those square-like artifacts. And we also want low and uniform correlation with your whole wave, with source lanes having roughly uniform contributions across the lanes. And those three goals are contradictory. So what do we do? And again, I will refer you here for details of the paper, but what we do, we run an offline optimization process that creates pseudorandom stochastic patterns. And those pseudorandom stochastic patterns, based on single parameter, sigma, try to balance those three desirable properties and produce patterns that are more like noise, more like blue noise, actually. And you can observe on the bottom of the screen example how a 3x3 deterministic pattern produces those square-like artifacts, while a 9-sample stochastic patterns is instead noisy, and most importantly, it denoises very well. We decorrelated those pixels. We have different masks for next time frames. They are also decorrelated across time. And it means that even vanilla TAA is able to successfully denoise this result. And this is all despite this method having worse PSNR than 3x3 or 4x4 regular grids. And this is worse PSNR not just on single sample before denoising, but also after denoising, which is kind of interesting. But this is the third takeaway here. The triangular patterns and correlations are difficult to denoise, they are perceptually noticeable. It's easy to miss this when looking only at numerical distortion metrics. And pseudorandom and stochastic patterns are a powerful tool to break those correlations. And I don't have time to go in details of the next component of decorrelating. I'll just very briefly mention that we already were using spatial temporal blue noise, but there was a great talk last I3D fast noise from Donnelly et al. So we took opportunity to evaluate some alternatives, as well as use our knowledge of the problem and domain, the fact that we're filtering within fixed screen grid, to try to also propose our own improvements, changing the pattern slightly, changing the energy, splitting function, etc. Please see the paper for details. I will skip here boring you with those. Instead, I'll just show the quantitative results. Here, our pattern marked with the red triangle performs the best on 2x2 patterns, 4x4 patterns, comparably on lookup tables, and fast noise performs the best on 3x3 patterns. So the fourth and final general takeaway here is that this off-the-shelf sequences, and again, state-of-the-art sequences like low discrepancy sequences or blue noise masks are good for general problems. However, many or most problems have unique properties, giving you an opportunity for improvement with some very minimal modifications. Very briefly, performance. The performance of our technique overhead comes mostly from increased register pressure because it's pure ALU and wave intrinsics. With 2x2, overhead is 0.04 milliseconds up to 0.14 milliseconds with 4x4. So to conclude the talk, some properties of our technique. First of all, we guaranteed that the quality is always better, or at least never worse than STF. Quality increases with increasing magnification, which is great because this is when you can see the difference more and better. It has cheap computational cost, is compatible with any positive discrete filter, such as bicubic B-spline filters, and also provides cleaner guide buffers for denoising. As a practical recommendation, I would say if you were to use STF, just do it. Just go with these improvements. especially when backwards compatibility is desirable and it works in any shader stage. And I recommend either quad 2x2 if performance is concerned, or 9 sample pseudo random lookup tables. Here, I'll start the video, hopefully. Oh, okay, I think the video plays. Yes. Okay, so those are general conclusions and takeaways beyond texture filtering. That wave communication is incredibly powerful, so is filtering in other domains than pixels. We advocate for custom Monte Carlo estimators for custom problems and understanding your problem and its error in the first place. We advocate for breaking correlations, and if you do some offline lookups, offline pre-computations, it can have literally zero additional cost. And we advocate for end-to-end system design, understanding your problem space. For future work, there are two main areas. One is generalization. First of all, whether this technique could also apply not just to bringing back filtering before shading, but also to filtering after shading when it's desirable. And whether our Monte Carlo estimator could apply to other problems, because convex linear combinations of multiple sources are pretty common and not unique to texture filtering. And the second main area is how to improve sample diversity. Because even with all those improvements and breaking correlations, we still sometimes filter exactly same pixels that don't bring extra information. And we tried some techniques such as defensive sampling, changing PDFs to more uniform, and they were improving some aspects but bringing artifacts. And the speed of light solution here would be if every lane sampled a unique pixel, but we leave this for future work. I would like to acknowledge here many of our colleagues across the company from research, DevTech, and other teams. And you can actually test this technique in NVIDIA's RTX texture filtering SDK, I believe. Some reference for the talk, and thank you. If there are any questions, we can do some now. And I will be also hanging around after this talk and my second talk here, happy to answer any end chat, and I have lots of backup slides. So yeah, thank you.
Great. Thank you, Bart. That's a great work. Yeah, any question?
So with the wave intrinsics, like what happens when one of the lanes is actually sampling a different texture from the one you want to filter? Like say, like it's some other object over here. How do you deal with that?
Cool. That's a great question. This is something that we had to consider. So if it depends when you are doing your texture fetching and texture filtering, right? Meaning that, for example, if you do this in a pixel shader, in a material pass, you're not going to encounter this problem. But if you were to do this, for example, let's say in a setup like Unreal Engine with the visibility buffers, etc., this problem is definitely possible. Then you need to, in this case, you need to use wave intrinsics to check if the material ID also matches between the two. One thing that we kind of noticed that even if we didn't do this, the technique works because UVs are sufficiently different then that the contributions of those sample will be zero. But it works kind of based on luck, not based on any guarantee. So I don't know if I would advocate this in production, but if you need to have like perfect guarantee that this error will not occur, then you would also use wave intrinsics to obtain the material ID and compare them.
And quick follow-up, does that, if you do the material ID thing and just use that to skip the sample, does that like mess up the weights that need to sum to 1 that you were talking about?
No, it will not, because generally the method itself has this renormalization, so it doesn't matter if effectively you end up filtering only from one lane, aka the pixel itself, or from full, let's say, 9 or 16 neighbors. The ones with 0 weights, they will be effectively discarded. But also, this is a good point because this is something that we discuss more in detail in the paper. The fact that some of the weights can be zero makes our estimator not consistent or not converge to the ground truth.
Thank you.
All right.
Yeah. Hey, I just had a question about the usage of the wave read lane like that's the usage that's shuffle, right, rather than broadcast. Like it's the lane index is a vector value rather than it being like a compile time or scalar.
Yeah, it's like a shuffle. It's just much more nicer API than shuffles. Yeah.
Did you actually try implementing any of the group shared versions? I'm just curious because like on some devices, like on Vulkan, for example, like it distinguishes between whether or not you support shuffle versus just broadcast mode, and some devices may not have that yet.
So we actually had a group shared memory version, not of this exact algorithm because we had like 6 different versions of it before we finally settled on this one. And we didn't attempt to perfectly optimize it. We are researchers, we are not experts on optimizations, but the performance was abysmal. It was like 20 milliseconds overhead.
I'm just curious too, because on some architectures, like some certain devices, if you're using like Wave 32 instead of Wave 64, you're going to have different behavior for broadcasting versus like shuffling.
Yeah, I think that if you want to target multiple devices with different wave sizes, I would probably just try to use like the lowest common denominator, or even as I've shown that even with quad intrinsics, the quality can be pretty decent and comparable to larger sizes. So with quad intrinsics, I think quad intrinsics are very attractive because they work in pixel shaders. Wave intrinsics also work in pixel shader, but depending on your rasterizer behavior, you know, like the pattern can be whatever.
Theoretically, if you use the quad stuff too, or like you might even work in DX11, you know, using like functionality.
Which is by the way how I first coded this. I coded this in shader toy with the DDX fine. I wanted to use DDX fine, but then I realized that WebGL does not support the fine version. It has only coarse version of the DDX, which is like, yeah.
Thank you.
All right. One question from me. So if we are going to execute this method in compute shader, you are assuming that compute shader execution is kind of tiled, right?
It can actually have like arbitrary layout.
Okay.
We don't really care for layout. We care for it if we want to have those optimized sharing patterns.
Right.
But even if it's completely random, it will work, just the sharing will not be as
so
effective.
it is not as effective as you execute like that. So
I actually tried it even in ray tracing shaders
that's something
for tracing shadows, and it also works.
Nice.
And you know, in ray tracing, like how are rays arranged? I don't know.
Yeah, it's completely
some driver engineer for sure they know, but I don't know.
Yeah. All right. Very interesting. Cool. Thank you, Bart. All right. Let's thank Bart again. And we are going to the last paper from this session, and it is GPU-friendly Laplacian texture blending from Bart again. All right, then, please.
Okay, thanks for sticking around for the last session of the day. And this talk titled GPU-friendly Laplacian texture blending. It's a paper that was published earlier this year in Journal of Computer Graphics Techniques, JCGT. It's an invited presentation, and I would like to thank here the committee of the conference as well as editors of JCGT for this opportunity of presenting the paper. It's a cool tradition. So yeah, thank you. So this talk will be about texture blending. And by texture blending, we mean we have one texture input, second texture input, and blend them 50-50? No, typically not. Typically when we talk about texture blending, we talk about mask blending. when we have some mask assigned to one texture, typically inverse mask to another texture, and we blend them for those spatially varying and adaptive blends and masks. And in this talk, I will focus on textures as images, as encoding arbitrary PBR properties, but I will not care about what's encoded in them. I will focus first on diffuse textures, but I will also show that it works for normal maps and other PBR properties. So let's not talk about physically based materials, physical material layering, interfaces, interactions, any of the cool stuff that people should be working on in 2025. No, it's about old school texture blending. So why do I still care about the stuff in 2025? Well, because it's so ubiquitous. Meaning that texture blending is used all the time by artists for complex material creation from multiple simpler materials that are combined together, for adding variety, for adding detail, breaking uniformity. It's a very convenient technique for memory footprint optimization, like for terrain textures where multiple tilers are blended together with low resolution masks. And it's also a pretty nice workflow. It's used for special and time-based effects such as footprints, weather, wear and tear, revealing contents, as well as texture synthesis and semi-procedural effects, decals, height blends, infinite texture tiling. And one of the papers about infinite texture tiling was my main inspiration why I started thinking about this problem. Namely, high performance by example noise using a histogram preserving blending operator by Heitz and I3D from SIGGRAPH 2018, where they propose a method to create kind of infinite varying texture from a single input example by picking random hexagonal crops from this input example, and then blending them on the hexagonal grid using, when those hexes overlap, using barycentric coordinates. I will not go into details of this paper. It's a beautiful paper. I recommend you read it. What was very interesting, their problem statement. If you do this kind of blending of the input, different random crops of the same texture, you end up with this completely washed out look, histogram that doesn't match the input histogram, and those kind of hot spots where contrast is preserved when there was no blending occurring. And again, the specific method they use is not as important here. It's a great paper, but they use local optimal transport and correcting histograms after blends. And this made me think about this problem, and I started to think, okay, this is a texture synthesis and one input. Doesn't it apply to general problem beyond single texture and to blending multiple textures? And of course, it applies here. So here are two textures blended with a mask with different levels of like blurriness or softness of the mask. And if we look, for example, at blends with very hard or sharp mask, it produces a natural and discontinuous look. If we use blends with a blurry and soft mask, we end up with similar problem. There is contrast loss, color loss, as well as feature ghosting, feature overlap of high frequency details. And matching simple statistics and histograms will help here. This will not solve the problem of ghosting. And what kind of histograms would be matching here? There are two different input textures. So how is it solved in practice? Because this is a very real problem. In production, artists tweak stuff until it looks good. Manual process, sometimes they just focus only on important regions. They use decals, skirts, and meshes to hide transitions or semantic blends. Meanwhile, research looks at addressing this problem either with methods for single texture like this correction after blend, smarter per pixel mask choices, or offline methods such as patch-based synthesis by example, or recently deep learning models. And I'll show here a teaser of the solution proposed here, compared to small blending radius, large blending radius, and our solution. Here is a wide blending radius with this that I shown before with feature overlap, ghosting, and contrast loss. And this is by comparison the proposed solution. that I hope you will agree that it looks quite natural and has none of the problems present in the wide radius. And the solution is almost off the shelf. It's called Laplacian pyramid blending. This technique was all over image processing and computational photography in early 2000s. This is a figure from Alexei Efros' course on image processing, specific chapter about image pyramids, where he shows how two images of fruits are seamlessly and very nicely, smoothly blended using this technique. And this technique gained lots of traction and popularity for HDR photography. And HDR photography where one takes multiple exposures of a scene, some that preserve shadows, some that preserve highlights, and tries to put them together in one low dynamic range image that preserves details. And if you were around or have seen HDR photos from early 2000s, they looked absolutely terrible. They were this toxic HDR look with gradient reversal, halos, weird saturation, etc. And exposure fusion paper, absolutely beautiful and seminal paper, was the first one, in my opinion, that solved this problem satisfactorily. The technique of exposure fusion that used Laplacian pyramid blending for blending those different exposures solved this. It was the first one to produce natural looking images. And today, if you have like a phone, like top Android phone, iPhone, whatever, the reason it takes beautiful photos, it's because it uses a variant of this technique or modern machine learning version of it. It was a revolution in computational photography that has allowed for replacing DSLR cameras. Okay, so before I explain the methods, very quick recap of Gaussian pyramids and Laplacian pyramids. Gaussian pyramids are created by successively blurring input image more and more. And because we're removing higher frequencies, we can downsample it without aliasing. Because because it's critically sampled, we don't have higher frequencies that would alias above the Nyquist. And this should look very similar to MIP maps because it's almost exactly the same. MIP maps typically don't use Gaussian filter. Typically they, I don't know actually what engines use nowadays. Back in my days, they use either terrible bilinear filter or some Lanczos or other filter. But other than this, it's very similar. And the reason for using Gaussian pyramids is the same as for MIP maps. It provides memory-efficient, memory-compact representation of the image that is pre-filtered, and operations on the pre-filtered version that have only low frequencies that correspond to coarse levels of a MIP map or a Gaussian pyramid are very cheap because they use very low memory bandwidth, and low spatial support in this MIP map translates to large spatial support in a finest level. Laplacian pyramids take the contents of a Gaussian pyramid before downsampling and take differences between each next pair of levels. And this difference means that the first level of Laplacian pyramid will have only the highest frequencies, the second level will have medium high frequencies, then medium, etc. And because the last level we cannot pair it with anything, we have the last level of Laplacian pyramid, which is actually a Gaussian filtered image. And similarly to Gaussian pyramids, Laplacian pyramids can be downsampled and compacted for efficient memory storage. And this is obviously a simplified version. In practice, it's typically done hierarchically, sequence of downsampling, upsampling, but this is irrelevant because I will show you later that we don't even need to construct those pyramids. But what is really important about Laplacian pyramids is that we can collapse them. What does it mean to collapse a Laplacian pyramid? Collapsing Laplacian pyramid means upsampling all those levels of the pyramid and summing them together. By summing together all those levels that contain all the frequencies of the input image, we can get it exactly back. And this property is extremely important and is the basis for Laplacian pyramid blending. In Laplacian pyramid blending, in the first step, we take the input textures and we create Laplacian pyramids of them. Then we take the input mask, which is a very sharp mask, and we create Gaussian pyramid. By creating Gaussian pyramid of the mask, we have each next level, each coarser and coarser level of the pyramid that is actually more and more blurry mask. And then we use this mask to blend each level of the Laplacian pyramid separately, meaning that the highest frequencies will be blended using a sharp mask, and the more coarser levels with coarser frequencies will be blended using more blurry masks. We blend those levels separately, we collapse the pyramid, and we end up with the Laplacian pyramid blending. And I imagine that from this description, it might not be yet obvious why this technique works. In the paper, I analyze it from statistical and signal processing perspective, but here let's focus on the intuition. Why does this work? To understand why it works, let's try to figure out what is the optimal blending radius. And what does it mean, optimal blending radius? So here are examples of bandpass filter: low noise, low frequency noise, medium frequency noise, and high frequency noise. And we have different blending radius, different harshness of transitions. And hopefully we can see this, probably not, I think it's already visible enough. We can see that the optimal blending radius is different for each frequency level. Low frequency levels have to use large blending radius, otherwise we end up with discontinuity. High frequencies need to use small blending radius, otherwise we end up with this contrast loss and kind of washed out thing in the middle. And middle frequencies want to use the medium blending radius. And with Laplacian blending, each frequency level uses different optimal blending radius. It's neither global nor per pixel, but it's per frequency band. And this technique is based in human vision and perception research. And the approach I described so far is definitely not real-time rendering friendly. We would need to create and collapse those pyramids, extra memory usage, bandwidth, maybe caching. It's complicated. So the main contribution of this paper is to how to solve this approximately at a very cheap cost inside of the material shader. I emphasized before that Gaussian pyramids are kind of like MIP maps, and this is the approximation and the assumption that I will use here. I assume that we have MIP maps of the input textures, which is generally true for materials in real-time graphics. And now, we can compute and blend Laplacians in place. Namely, we don't need to create Laplacian pyramid. We can upsample MIP level n and upsample MIP level n+1, take the difference, and this is our Laplacian. And we can use hardware bilinear upsampler for this, which is not great for anti-aliasing, but it's super cheap. And that's literally the whole technique is presented here. That's actual code. It's not pseudocode. It's code of the technique. You can check this code both in the paper as well as the live WebGL demo that's on JCGT website. I'll just highlight it here that those different levels of Gaussian pyramid of mask are simply different MIP levels taken from the mask texture. Laplacians are differences between samples from consecutive MIP levels. It's blended inside of the loop over the number of levels and returned inside of the material shader. So that's the whole technique. And I mentioned that this is an approximation, right? So is it different from a high quality reference? Probably side by side, it's not very visible if there is any difference. So I will go flip back and forth. So it is definitely different from the reference because of the use of the bilinear upsampling filter. But it's not that one is significantly better than the other. I tested it on many textures and it looks just as fine and as comparable. The technique has one parameter that I propose to expose to artists because it's crucial for the final appearance: number of the used Laplacian levels. The more levels you use, the wider is going to be the final levels transition radius. Meaning that if you use two Laplacian levels, you can still end up with this relatively harsh cutoffs that look better than small radius without Laplacians, but still are not perceptually perfect. With 4 levels, things start to look very natural, and overall, in most of my experiments, I use 4 levels. And with 6 levels, I think it looks like just one texture. It looks like there was no blending happening whatsoever, which can be really cool and desirable. It depends on the artist's intent, because now rocks have taken a bit of color of the other surroundings. So this is why I think this should be an artist-controlled parameter. And I mentioned this technique also works for other properties, such as normal maps and roughness, etc. I'll show here the normal maps. And I will discard the large blending radius from comparison because it shows visible ghosting. So let's compare small blending radius and our solution. And the difference here will be a bit more subtle than before, but hopefully it's visible in those regions. And if you look at small blending radius, when there are smooth or flat surfaces that are touching and contacting, there is a visible discontinuity that would be very visible when applying specular shading. And by comparison, our technique flattens this out, producing more natural look. And in fact, it resembles very closely normal detail mapping. And as funny anecdotal observation, when I was trying it, it seems that normal maps seem to require less renormalization with this technique. And it goes beyond normal maps. Encoded semantics do not matter as long as frequency decomposition is valid. So if you're using binary mask that has to be 0 or 1 for some property like metalness, this will not work because you cannot take Laplacians of binary mask, or you can, but it will not be valid. But it's for any other properties, it works just fine. But one interesting observation is that it looked kind of differently on normal map as compared to diffuse texture. And general observation is that Laplacian blending is content dependent and content adaptive. It will depend on the frequency content of your textures. And normal maps tend to have higher frequencies than diffuse textures, and the result will look slightly differently. As a fun, very wild bonus, very weird blend of normal map and diffuse map. But what I wanted to emphasize is just like on the right, if you see like the rocks are much better preserved, while the color blends much more smoothly. And this is general. This exaggerated example shows you the behavior of the technique. What I mentioned before is that I wanted to have option of artists using dynamic masks or time-based masks. And because of this, I would not want mask to have to regenerate mid-maps anytime they change some parameter. So an approximation that I propose here is that instead of creating this harsh mask and creating MIP chain, start with a soft mask or even a distance field. This technique is inspired by distance fields. And I apply a custom soft thresholding function that approximates blurring. And details are in the paper, but by adjusting the parameter of like the transition zone of the soft thresholding, you can approximate blurring of the mask. So it works with, for example, weather effects and other similar. The technique works with minification as well. Just skip the first few Laplacian levels that are not representable on screen, meaning that the technique allows this itself kind of naturally and automatically. Beyond some distance, there is no Laplacian blending required at all. It works obviously with multiple input textures. You just use multiple Laplacian pyramids. But with multiple Laplacian pyramids, multiple PBR maps, multiple masks, you can end up with a lot of texture samples. And I would say this is the biggest downside of the technique. While those samples need negligible additional bandwidth because they are from lower MIPS, they will cost register pressure and they will cause pressure on your texturing unit. So even on a powerful GPU, if you start going with 7 levels, you start observing some performance overhead. So some suggestions how to improve it. One that I find not very satisfactory, but it's possible. You can always cache blends, especially if you have virtual texturing system. You can use this soft mask technique to avoid taking additional blend map samples. But the main and most interesting optimization technique is that you can actually skip some Laplacian levels. So, for example, you can say that Laplacian level n is taken by MIP 2n minus MIP 2n plus 2, effectively combining together each consecutive pairs of Laplacians. So this is an approximation. Does it work in practice? I was surprised, but it has very negligible quality impact. Absolute difference is very small. And if we flip back and forth, it might be visible or not. There is some difference, but it's very, very small, with 2 levels being skipped. If you were to skip 4 levels, it starts showing ghosting, and I don't recommend it, but 2 or 3 levels skipping is a decent optimization. So some discussion and recommendations. Properties of this technique. It uses local neighborhood and per frequency local neighborhood. So decisions are neither global nor per pixel, but this local context allows us to make better decisions for blending. There is no pre-computation required, just presence of regular MIP maps, no training, learning, statistical analysis, and we're not correcting blends, we're blending in the correct space to begin with. Pros of the technique. It's adaptive, it's automatic, there's single parameter, it adapts automatically to the contents, and most of the time it looks exactly as it should. It's a very simple drop-in, very simple shader modification, no pipeline changes or anything like this, and looks very naturally because origins of those techniques are founded in perceptual research, and again, your mobile phone uses technique like this. From cons, it's adaptive and automatic. I repeat this point again as a con because it leads to possibly surprising behaviors and limited artistic control. One parameter might not be enough. And it has some additional performance overhead that can be worked around, but it's not perfect. So is it for you? First of all, you can check the WebGL demo. It's also on the project website. It doesn't run on every mobile phone, but on every laptop and should just fine. I think it's just another tool. It's not a tool to replace other tools or other ways of blending or workflows, but I think your artists, if you work with artists, will find it extremely useful and find some cool creative uses. Just expose it in the engine or your toolbox and see what they come up with. If it's too costly, it does not need to live in final shaders. It could be just used during content creation time. And in the paper, I actually mentioned some ways of adjusting the look and tweaking it to make it more custom. Finally, some takeaways looking at bigger picture beyond texture blending and Laplacians. So first of all, I think that those kind of local effects are extremely powerful. And they are bread and butter in machine learning, computer vision, image processing, convolutions, pyramids, units. They are kind of underutilized in real-time computer graphics. And this local context is extremely important to make good decisions. And I think it's a sweet spot between single pixel and global processing. Secondly, frequency space processing can be easy and affordable. And why I say this, I also will say something that's maybe hot take. Maybe we can discuss this after the talk. I think that DFT or FFT are kind of useless in real-time graphics. And it's not just because of performance. Okay, rendering, maybe not graphics, because they have definitely uses in simulation, etc. In rendering. And it's not just because of the cost, but because of assumption of periodicity, boundary condition, infinite spatial support, ringing, all those things that don't align well with perception. However, frequency space processing doesn't mean DFT. It can be Laplacians, it can be wavelets, and they are great, affordable, parameters are very memory efficient, and they offer higher quality and better perceptual effects. And finally, I encourage you to read papers from other computer science domains, like here computational photography or computer vision. They have a lot to offer. Just read the literature and get inspired. Don't get discouraged by computational costs. Focus on what are the key insights. Can you apply some of those ideas in your domain? And with your expertise in real-time graphics, in real-time simulation, and making things real-time and fast, I'm sure you will make them fast. So, okay, thank you.
All right. Thank you, Bart. That's a very elegant solution, and I like your paper. And yeah. All right. We don't have much time, but yeah, maybe we can take one question.
Okay. So just point of clarification. Laplacian pyramids were developed, the theory and the implementation and everything, by Peter Burt, that she first published in 1981. And there's no coincidence going on here. That work inspired Lance Williams to then come up with pyramidal parametrics, also known as MIP mapping, which he did because of Peter Burt's work in 1981. And in fact, reading Peter, including Peter Burt, had the iconic apple and orange picture in his 81 work. And in fact, that also inspired me to come up with band-limited noise. So everything that you're doing,
everything connects,
rehashing in a really nice way what people were focusing on a little over 40 years ago.
Yeah, the noise is not a coincidence here, right? So,
yeah, of course.
Yeah.
And David Lowe, who was my thesis advisor, was actually writing a review of work that had happened about 2 decades earlier when he talked about it. He would never take credit for any of that. So,
cool.
So this is great that over 40 years you're putting it into NVIDIA.
Thank you for the comment.
All right, then. Yeah, one more question here. Let's take one more question.
So I guess your normal map example, those were just standard tangent space normal maps?
I actually downloaded some open source assets. I don't even know what space they are, but I believe they are just normal tangent space. But it should work with other like derivatives. And
yeah, exactly. I was thinking normally when you blend normal maps, it's best to do it in slope space. So x over z and y over z. So that actually kind of makes a case for having that as your normal map format, because then you just directly got those as MIP maps. And then if you're doing all these extra taps, and you're saving maybe some channels to read and so on. Cool.
Yeah, and it also has a property that if you do just derivatives, I think they would have even sharper spectral slope, like even higher frequencies, and they should blend even better.
Yeah, that's what I was thinking. Great.
All right, then let's thank Bart and also other speakers in this session again.